After all that, 53 slides is roughly what we've got left, right, which I believe covers everything.
Nice.
My general pace is 10 slides per lecture. I have to go faster than that. Okay? So we'll see what happens. The big section we're moving into is our addition reaction with electrophiles. Right? Almost all of the addition reactions with electrophiles involve some kind of cyclic intermediate. Right? When we looked at the addition reactions with acids, the acid was our primary reactive species. We react the acid H+, we have a cation, and then we can cascade the rest of the reactions. When we're looking at our electrophiles, to get a positively charged atom other than hydrogen, we end up having to add weird kind of caveats and oddities into our structures, and that usually results in these kind of weird cyclic intermediates. Okay, so I broke it down according to what type of cyclic intermediate we're forming. Okay, so we have a tri- or three-membered cyclic intermediate, four-membered cyclic intermediates, and five-membered intermediates. So we're looking at those results and how those things transition. You'll notice that I've got different colors highlighting what's happening within this, right? And that's coming down to the atom that's causing our cyclic intermediate. In the case of the tri, we have our alkene, so there's two atoms right out of the gate. Right? If we're going to do a tri-cyclic intermediate, we're looking at bromine being the extra atom. We're looking at P in MCPBA, which is a little bit weird because MCPBA is the nomenclature of that compound. The P is referring to a peroxy structure. It's an oxygen that is our third atom. CH2N2, carbon is our third atom. And then mercury, X2, because usually the X2 will be a variety of different pieces that we aren't too stressed about. But mercury will be our third atom. Okay? If we move into tetra intermediates, there's fewer of them. We really only have our hydroboration. So we'll be adding hydrogen and boron in our cyclic transition state. In the five-membered rings, we'll be adding osmium and oxygen as a reagent. That gets a little bit weird because we go through and look at these. The osmium and oxygen adds two atoms. There's two in our alkene. Where's the fifth atom if we're getting a five-membered ring? It's a second oxygen from the OSO4. So it's an osmium and two oxygens involved in the five-membered ring. Permanganate, it's the manganese and two oxygens in our five-membered ring. And then ozone, O3, all three oxygens get involved in that five-membered ring, and that one does some weird, gnarly stuff. Okay? So what we're focusing on is trying to find our electrophile, finding our nucleophile, and seeing how these react. Okay? How did the alkene react? What makes the alkene reactive? The pi bond. What's in the pi bond? Electrons. Electrons, which mean our alkene is acting as a nucleophile. If it's acting as a nucleophile, then the very first step in all of these reactions is those pi electrons reacting with some electrophilic atom. Okay? So in all of those cases, what we are trying to find is an electrophilic atom. What makes an atom electrophilic? A positive charge. If we go through and look at all of those situations, we'll find that those positive charges aren't super obvious. Okay? The only one that I would argue is obvious, which is a long shot, would be our tetra intermediate, the B, and HBX2. Why is the B the electrophile? What is B? Boron. What is special about boron? If we look at a Lewis structure for boron, it is satisfied under its octet, which means the hybridization of boron is sp2, which means left over is a p orbital that can fit electrons. Okay? So when we're looking for these charges, or these positives, that one's probably the most obvious because we go back to our hybridization effects. And I said, well, that wasn't that obvious. You're right. Okay? It's not obvious. And that one was the most obvious. Okay? So that one has the most positive aspect that we can think of. It has that empty orbital where it can dump electrons. How could bromine possibly be a positive? Or said another way, how can an atom obtain a positive charge? It has to lose electrons, which means what needs to happen? Something must take the electrons from it. So if we look at the structure of our electrophile, it is likely bonded to, in our starting system, something that is highly electronegative. If I look at Br2, I have bromine bound to bromine. What's a characteristic of bromine? It's electronegative. So if one bromine sucks the electrons away, the other one becomes positive. There's our positive atom. In MCPBA, I set up peroxy. The peroxy acid is this structure. That oxygen ends up being reactive because we might look at the OH bond, but it's actually the OO bond that's the more interesting one. The OO bond, because we now have the second most electronegative element on the periodic table bonded to itself. That bond becomes exceptionally polarized because of the oxygen-oxygen bond, and if that oxygen takes the electrons, what's our result? Yeah, we'd have a positive oxygen. What's special about the negative oxygen? Resonance stabilization. So we have an insanely good leaving group. That gets us our positive oxygen. Right? The next one down, our CH2N2. Okay. That one's a bit of a weird one. Guess what the carbon acts as? An electrophile. Why is that weird? It has a negative charge. Why can it act as an electrophile? What's the result of that arrow? We'll draw the carbocation temporarily. What is this species? N2, gas. How stable is nitrogen? Insanely stable as a gas. That nitrogen-carbon bond is dying to break. Okay? It is so reactive that people lose fingers when using this reagent. Yes. Okay. We'll look a little bit closer at that one later. It's known as a carbene. And then our last one. This gets really fun. Mercury. Why might we have issues with mercury? We could say a liquid. Right? So it's already weird. It's a metal. It's a liquid metal. That's all sorts of strange and bizarre. It's also a transition element. It's also way outside of that realm of elements that I said we ever needed to worry about in OChem. Okay? Why? Because mercury does some weird, funky stuff. And one of those things it does, those X groups are electronegative enough that they can suck electrons away from the mercury, making the mercury positive. It can then interact as an electrophile. Same kind of concepts are going to go through with the rest of those reagents. Okay, so let's kind of poke through and see what we can get. So, our electrophilic additions, breaking it down into two big kind of categories. We take a look at our Lewis acid, okay, or our electrophile. Okay, is it a nucleophile also? How would I be able to tell if it was a nucleophile also? What would it need to have to act as a nucleophile? It needs to have electrons. So if I look at my reagent and I say that that structure, okay, can accept electrons because it's positively charged, but then at the exact same instant it also has electrons, those electrons can immediately react back with the structure. Right, well, why would it do that? If the electrons come out of that pi bond, whoa, was kind of a big eraser. And we said the electrons hung out on one carbon in preference to the other. That one would be our negative, which means the other carbon is positive. So if we look at our reagent and we say the Lewis acid is a nucleophile, for it to be a nucleophile, it must have electrons. First and foremost, it must act as an electrophile. Okay, so we're looking at kind of a weird situation. If that happens, what we end up getting is this three-membered transition state, or this three-membered intermediate. Okay? That three-membered intermediate has the potential to now react. Why would it react? Bond angle is terrible. Okay? We're looking at the carbons at very least being sp2 hybridized, or sp3 hybridized, sorry, and they're now being constricted to a 60-degree bond angle to make a three-membered ring. So there's a bond angle thing that's unhappy with it. We had a suggestion about octets. Octets gets a little bit questionable because the carbons octets are satisfied. The octet that would be in question would be the Lewis acid, and I don't know what the Lewis acid is, so defining the octet's a little bit questionable there. But the Lewis acid acted as an electron donor, right, and an electron acceptor. Maybe that Lewis acid doesn't want to be positive. Okay? If it doesn't want to be positive, then what can happen? Our nucleophile can come in, attack, and shuttle us out to a final product where we've fully broken everything apart. Okay? So what we need to do is look for our reagents and classify them into these sections. What happens if our leaving group is now tiny? Right? So if we look at the bottom situation, this comes in, attacks the Lewis acid, and then the electrons go to the leaving group. If our leaving group is tiny, is it stable? No. Which means, what is it going to immediately try and do? React with a positive charge. What's happening with our alkene? We're forming a positive charge. So what will end up happening in that case is that our leaving group will immediately come back and attack the alkene at the exact same instant. Okay? And that'll set us up with a new product. Could we potentially go on from there? Yes, that's going to depend on our reagent. So we have multiple questionable states at each of these positions, and until we define what our reagent is, we aren't going to be able to figure that out. Okay? Can we already start to call attention to some regiochemistry? Take a look at the three-membered ring, the nucleophile and the Lewis acid. Would we expect them to be on the same side or opposite sides of the old pi bond? Why opposite sides?
Because of the ring.
The three-membered ring, when that ring forms, it can form either wedged or dashed, but let's say it's wedged. That second bond must be wedged, which means when the nucleophile comes in, it must be coming in dashed from the back side of that bond, which means the arrangement between the Lewis acid and the nucleophile will be a trans alignment. They'll be on opposite sides of our old pi bond. What about the four-membered transition state? So people might have been able to cheat with the three-member transition state because we did it in lab. Now you can't cheat because we haven't done this one in lab. Now you're trying to envision things in 3 dimensions, so let's think about it in 3 dimensions. We have our pi bond, our 2 electrons, right? And then we have our Lewis acid and our leaving group. Take your pick, doesn't really matter. Electrons can come out and react with one. Wow. And then we'd have the leaving group.
Super reactive.
Okay, so it came in from the top. The leaving group is now chilling up here. If the leaving group is insanely tiny, is it stable? What is it going to try and find? Something to stabilize it. The positive charge that just formed on the alkene. What are the odds that that negative charge that is insanely stable goes like this? Not very likely. It would somehow have to wrap around. Physically, that's not likely to happen. So instead, where does it go? Immediately connects, and the leaving group and the Lewis acid are now attached on the same side of our starting double bond. And we end up with a cis alignment of our structures. Right? So the regiochemistry falls out of our mechanism. So when we're looking at these, we do have to know the overall addition reaction, and that's what's being summarized on the bottom. We have to look at the addition reaction due to the loss of the pi bond. That predicts our products. Right? Our positives and negatives matching up with Lewis acids and leaving groups will assign the relative location of our leaving group, or of our regiochemistry. Right? But we'll have to evaluate the structure and the mechanism to see how the stereochemistry aligns and something about the regiochemistry. Or you've memorized the crap out of everything. Right? 2 weeks, you can try and cram it. So let's take a look at the three-member transition state. How can the structure be both an electron acceptor and a donor? Okay. So we're going to need a couple different things. Number one, we need lone pairs. Why do we need lone pairs? It needs to donate electrons. Okay? If it doesn't have the electrons, i.e. no lone pair, then it can't donate the electrons. Okay? So we need to have an atom that has lone pairs. Okay? We also need very weak bonds. Why do we need very weak bonds? So the bonds can break easily to generate the electron acceptor. So what we're trying to do is look at our reagents and say which of those things match. Okay? So we've seen this before. Our alkenes do this. Okay? We have kind of lone pairs. We have pi electrons. Okay? And we have very weak bonds. They aren't really very weak because it's an alkene. But due to resonance, we can see that we've formed a negative charge and a positive charge. That matches what we're looking for. So alkenes act as this. Alkenes do this, but that's a larger structure. So we want to see smaller structures. Okay, looking at those reagents. Okay, and to bring everybody up onto the same page, we'll go ahead and do the lab example first. Br2. Does Br2 have lone pairs?
Yes.
I have lone pair electrons on that bromine. Does it have a weak bond? The bond between the two bromines. Bromine is very electronegative, which means what is it doing to those electrons? Pulling on them. It's trying to hold it. So all we have to do is provide a slight polarity to this, and what happens? The bond breaks, the electrons shuttle off to the bromide. Bromide is now a stable, good leaving group. Yes, I've satisfied this. Br2 works for our three-member transition states. How about CO2? Why not? Okay. We have lone pairs. Could we shuttle those electrons to the carbon? Why not? Oxygen is more electronegative than the carbon. It would keep those pi electrons. So we don't have a good structure in CO2. What about the last one? Where do we see lone pairs? Okay. They're actually drawn on there. We could also look at the ones that were implied. Okay. Let's call them the red lone pair. Would I expect those to fit this pattern? I have lone pair. Do I have a weak bond to that oxygen? I've got that pi bond. The electrons would have to shift to the carbon. That's not going to happen because oxygen's more electronegative. So we can erase those. How about the now purple ones? Those electrons would have to shift to that carbon, which it doesn't break octet. Oxygen's more electronegative. That doesn't push the electrons the way we would expect. So those electrons don't make sense. What about now the red electrons on the mercury? Do I have a situation where I have a weak bond? What could those electrons do? Now highlighted in red. They could move to the oxygen. Well, is that a fair maneuver? Yeah, why? I don't quite accept mercury likes to be positive. Oxygen is more electronegative than the mercury. Those electrons are already moving that direction. Take it a step further. What happens if the oxygen takes those electrons? Oxygen becomes negative. Oh, we can't have a negative oxygen. That's a bad leaving group. There's resonance stabilization. So that mercury reagent does fit the pattern that we just discussed. That mercury can act as our electrophile and our nucleophile. So it's looking at the pieces and trying to line those pieces up. Right? So what happens when we go through and look at this? Well, we've got the pi bond. The issue with our pi bond, the electrons can come out and either attack from either side, which means when we go through to look at our final answer, the relationship between our structures could be different. We have to be aware that when we're doing alkene reactions, we have the potential to form two products. You have to look at both. Right? So what happens, our electrophile reacts with the pi bond. The leaving group leaves. We end up with generally a negatively charged leaving group and a negatively charged nucleophile, maybe. We have the three-membered transition state. What can now happen? Our leaving group or nucleophile, whichever is stronger, can come in, do a backside attack, and kick out the electrophile. And we end up with our product. Make sense? Questions about it? Okay. Why are we showing all those again? Oh, we have a new one. BR2 had the ability, because it had electrons and we had that weak bond. What about CH2N2? Right, this one helps if we draw out the Lewis structure. There's our basic skeleton. How many electrons need to go into our structure? How do we figure it out?
3 sets.
So I heard 20, I heard 3 sets. These numbers are not matching. Total. Carbon has how many electrons? Hydrogen has 1 times 2. Nitrogen has 5 times 2. Ooh, that's 10, sorry. And we get 16. How many are already drawn in my structure? Where do I put my next pair of electrons? Which nitrogen? Ultimately, it's not really going to matter which nitrogen I put it on. How many electrons are now in my structure? 14. I need 2 more. Where do I put the next 2? Next nitrogen. We check octets. What happens? Okay. The nitrogen's lacking and carbon's lacking. How can we fix? Where do we want to make double bonds? Carbon, nitrogen, so presumably you're saying that. And then?
I want to do a triple bond on nitrogen and a single bond on carbon.
What is the result now? Have we drawn a valid Lewis structure? What's wrong with it?
Nitrogen's too many electrons on that one. It makes it negative.
Have we assigned formal charge? No. So if you want to start complaining that the formal charge is bad, that's one thing. That doesn't invalidate the structure.
Then the structure's good.
Okay. So let's finish off the formal charge. Where's our formal charge? Nitrogen would need to be a negative. And the other nitrogen would be positive. People don't like that? What do you want to do? Drawing what? Resonance. Yeah? Oh, we get two resonance structures, both of them with charge. Yes, you're right. We do. Okay. Which of those two structures is better than the other? Okay. It's kind of a hard question to answer. Okay. Why would we say that's a hard question to answer? They both have a positive charge on the nitrogen, so we can't evaluate that. What should we be looking at? The negative charge. Where should the negative charge be more stable? On the nitrogen. Okay, so we might suggest that this is our first or our best structure. When we're looking for reactivity, what should we be evaluating? The first worst resonance structure. The one that we've underlined is the best one. Which one is the first bad resonance structure? The right one. When we go through and look at that, that carbon has a source of electrons. Not only that, but if we shuttle those electrons to that positive nitrogen, nitrogen doesn't want to be positive, we also have a weak polar bond. That reagent fits the same category. We have a reagent or an atom, the carbon, that can act as both a nucleophile and an electrophile. This reaction generates a very high energy intermediate in that carbon. Okay? That carbon ends up having very particular chemistry, or such interesting chemistry that it gets its own name, is referred to as carbene chemistry. The carbon acts as both a nucleophile and an electrophile. Okay? It does have its octet. Okay. Where it becomes interesting is that sometimes, if we're lucky, we can generate the carbene with the leaving group having already left, and that would be the structure that we would draw. And this is what Joey's then complaining about. Is that structure negatively charged? Is it positively charged? It's neutral. What the hell? Yeah, it's neutral. But what's its hybridization? sp2. Okay, what's in the extra p orbital? Nothing. What could I put in that extra p orbital? Electrons. There's the electrophilic characteristic of our carbene. Because it has the lone pair, it can also act as a nucleophile. There are a variety of ways to build these. CH2N2 happens to be one of the more common ones. Okay? But what we're looking for is the ability for a good leaving group to come off of that. Okay? Our peroxy acids will do the same thing, right, which we looked at. The oxygen with lone pair electrons can act as a nucleophile. But at the same time, the bond between the oxygens is weak enough that I can break away. And that red oxygen can act as both a nucleophile and an electrophile. Okay? Mercury does the same thing. Okay? Neat reagents, a bit challenging to work through, but they're there. Okay? So then the question is, does it continue? Okay? So on that next question mark, we said, should we have the nucleophile even come in and attack? Is that relevant? So deciding for that second step, we have to ask, is the three-membered ring I made more stable or less stable relative to our nucleophile? That's kind of a challenging question, so let's look at some potential examples. Okay? If it is stable, then we're done. Stop the reaction. We don't need to continue. If it is unstable, then you need to run the nucleophilic attack with whatever nucleophile you have accessible. Okay? If you're not sure, run the nucleophilic attack and predict the products. Compare your leaving group to your nucleophile and decide, was that useful? Okay, so in that first box, what do we have? We've got our three-membered transition state, or our three-membered product, the oxygen in the middle, and then we have our nucleophile down here. Is that three-membered ring stable? You're saying yes, Amanda. Why? There's no formal charge. So yeah, we do have the ring structure, a three-membered ring, which puts some strain on it, but there's no real added benefit to breaking that open. Right? There's no charge. What about the nucleophile? The only thing that's negatively charged right now in solution is now that species, which came from our peroxy acid. Is that a good nucleophile? Why not? Resonance stabilization neutralizes that as a nucleophile. So what happens? Our reaction stops with the three-membered ring. How about the next one? So this was the product that came from this guy. This one came from BR2. What do you think? Three-membered ring, stable, unstable? Unstable because? Charged. Okay? So, if it's unstable, what should we do? Stabilize it by running the nucleophilic attack. Okay? Do I have a negative species floating around? Yep. What can happen? Donate the electrons, break the structure open, and we'd have our final product. So we do continue. What if you're unsure? Let's take a look at that final one. Okay, what do you think? According to our stability argument of neutral, it is neutral, but that's a cyclopropane. That's not particularly stable. We said the epoxide, or the three-membered ring with the oxygen, was stable. Okay, so that's a little bit fishy. And then N2, I don't know. What happens if it attacked? What would we get? What would the result be? A negative carbon, good. And positive nitrogen. Did we make our structure more or less stable by doing the attack? Less stable. A lot less stable. What does that mean? Don't do it. Stop it at the three-membered ring. Okay. So what we're picking up in the tail end of this semester is now looking at the reagents and the pieces and trying to evaluate and predict what's happening. Not just a rote memorization of the reagents, but looking at what you produce and then testing it. Yes?
So the excess of carbene triggers that reaction?
An excess of carbene isn't going to react with anything. The nitrogen is a gas, bubbles out of solution. The cyclopropane, assuming it stays in solution if we were cold enough, okay, will stay in solution, but it doesn't have anything to react with the carbene because there's no pi bond. Okay? So what we're trying to do is look for those patterns, evaluate those patterns, and predict from those. So here we go. Practice with your cyclotri-electrophiles. 1, 2, 3, 4 questions. 4 questions seems reasonable for a quiz. So this is one of the things that's going to become really important is looking at the reagents and trying to predict what's happening within the chemistry. So what I broke down in those few slides right before this was looking at the individual pieces and saying, what should I be thinking about when I approach this? There's too much information to try and just say, this is everything that's happening. So what I'm trying to do is provide you enough context that you can propagate that material out into situations that you haven't seen, which is really what's happening with question, I guess, 3, which I've now erased. So our alkene will attack. Okay? That exceeds the octet on the bromine. That breaks. Because the original bromine, we'll call it our red bromine, has electrons, those electrons can immediately come back and attack. Okay? The result is that you get this. We form what is known as the bromonium ion. It is the bromonium ion that explains why we don't get hydride shifts. Because when do you get a hydride shift? Carbocation. That's not a positive carbon. It's not there. Okay? So then we can say, is that the final structure? That is a horribly unstable structure because positive charge on the bromine. So we want to fix that by looking through the rest of our solution. What do we need to find in the rest of our solution? Electrons. What else do we happen to have floating around? Bromide with a negative charge. Cool. What can that do? That can backside attack. Which carbon? Oh, please don't fail recording. Which carbon? There isn't really a big difference, so don't worry about it. What's the result? We have a bromine. So here I'm attempting to show the anti-alignment. This is already a problem. I can't show the anti-alignment here because no. The anti-alignment is with respect to the bromines, that one is up and one is down. Isn't that what I showed? I haven't specified stereochemistry on that. I can show the up and down. That is fine as long as the up and down are very clearly referencing up and down, which means only two solid lines shown for each of those carbons. How many solid lines are shown for the carbons? The carbons of our alkene. How many solid lines are shown to those carbons? 3. Which means the up and down that I'm showing with the bromine, completely invalid. Right? That does not mean up and down. That just means I drew them that way. That's it. Right? Which brings in the next important part on this. Right? We really only care that they're up and down if and only if I need to specify it. Well, why would I need to specify it? They're chiral centers. Well, are they chiral centers? Yes. Crap, I do need to specify it. Which means instead of showing 3 solid lines, I must show 2 solid lines, a wedge, and a dash. Have to. No choices. Okay, so I'm going to show the bromine up here, wedged, and the bromine down here, dashed. Now I've specified very clearly an anti-alignment. One is up, one is down. What is the problem? It could be either way. Because it's an alkene, there's 2 possible products. I get the other alignment as well. Okay? I have to show both. Okay? So when we put together our drawings, we have to be cognizant of how we're representing our structures. Okay? The instant you want to show wedges or up and down the spatial arrangement of atoms, you need wedges and dashes. But just because you want to show it doesn't mean it's relevant to show it. Okay? In this case, it is relevant. We would have to specify it, and we'd have to say that we get 2 products out of this. Questions about that? This is the part that makes it exciting and really crappy all at the same time. What happens with what I've labeled as number 2, which I believe is the bottom one? We said we needed to identify the important atoms. In the top one, it was bromine. In the bottom one, it's mercury. Mercury reacts. Let's kind of erase some of that. There's a question about what the OAC meant. In purple is an acetyl group. So if we have an O-acetyl, that's what we're representing. The pi bond can attack the mercury. That bond is a polar bond because it's a great leaving group. And this is where mercury gets nasty, because typically when we show this, what is being implied? Electrons on the mercury. Why is that of critical importance for this? The electrons from our mercury can immediately share back. Which means, what do I produce? I've produced a ring with the, that's supposed to be an H. And that's an eraser. Let's try that again. So far, so good? Right. Is that a stable product? Why not? It is charged. We need to fix that charge, which means what do we need to find? Electrons. Well, what electrons do we have floating around? But I just drew acetate. Why are you guys saying water?
Because those resonate.
The acetate has resonance, which neutralizes its effect as a nucleophile, and it's got to be the electrons from water that are now going to attack. Where are the electrons going to attack? Backside, which carbon? Ooh, this one becomes challenging.
Secondary.
This is going to come down to that leaving group. Is it a good leaving group? Does mercury want to be positive? No. So it's trying to leave the structure already. So one of those bonds is already weakened. Which bond would already be weakened?
The secondary.
Why the secondary one?
Because I would leave a more.
That would leave a more stable carbocation. It does not form, but it's leaving that as a more stable species. So the bond between the mercury and the secondary carbon is now the weaker. The next part of it, if you don't like that argument, we have another argument. Water is acting as a nucleophile. And the nucleophile is now attacking at a carbon where we have a leaving group leaving. Ooh, interesting. That sounds kind of like substitution. What kind of nucleophile do I have? Weak, which suggests which mechanism? SN1. Which carbon should I attack? The one that would form the more stable carbocation. It's attacking the secondary position, not the primary. The result. Sorry. Thanks for the what? And I was drawing it all nice and pretty too, and now it looks all ugly. Does oxygen want to be positive? No. What can happen? And what do I have? I have the final answer for this. Right? That's what was being asked for. What some people have been doing is because you read ahead in the textbook, you're now jumping ahead to the next step, which involves literally a next step. Instead of it just saying mercury, acetate, and water, I say step 1 is mercury, acetate, and water, and step 2 is sodium borohydride. Sodium borohydride does a bunch of extra crazy chemistry. Do we want to look at that crazy chemistry yet? No, so don't worry about it. Focus only on the reagents that are at hand. Right? That ends up being our product. Do we have to worry about stereocenters?
Yes.
Do I have to worry about it where the mercury is? No, I'd really only have to worry about it where the OH is.
But don't you have to show
Right.
that they were anti to each other?
Which would then be the anti-alignment, and if the mercury is not relevant, that makes the OH not really relevant. Do I still have to be concerned about the OH? Why? That atom is a chiral atom. I would have the OH both wedged and dashed. The mercury I won't worry about because it's not a chiral atom. Okay? So I would end up with enantiomers with that product. Make sense? Okay. So what we're trying to do is stepwise through and just look at how these things can potentially react and start scaffolding it. Okay? What you can do is just rote memorize. You are fine with that. The issue with the rote memorize is that doesn't establish all the chiral atoms. If you've got something like 10 new reagents to memorize, you then also have to identify all the chiral species, the arrangement of all those groups, and that becomes challenging. Okay? Because you're not just memorizing those 10 things, you're also memorizing the rest of the semester. Right? So what I'm trying to do is set you up with the tools to be able to process and think your way through. Whoa, come back here. Top one, what's happening with the top one? What does the alkene act as? A nucleophile, which means we would need to find an electrophile. Do you see any obvious electrophiles? Where's your obvious electrophile? The NaOH is an obvious electrophile. Does everyone want to agree with that statement? Why not? Hydroxide. So I agree, jumping to the hydroxide is probably a good idea here. Instead of going, oh, I need to do an addition reaction, let's work with the alkene. Let's say face test. Alkene, I don't know. Chloroform, I don't know. Hydroxide, I'm going to be a little bit upset about that one. That's going to melt my face. Okay? So negatively charged oxygen, what do I need to find? A positive charge. Does the alkene give me a positive? No. Well, if the alkene doesn't give me the positive, where's the positive? It's got to be up here. Where's my most positive atom up there? Probably the hydrogen. I have no idea why I just drew that weird. What connected the dots? Because I did not do that. And you might say, well, that just made things worse, Mike. We have more negative in another alkene. Hydrogen wasn't acidic enough to react with the alkene. What? You're saying you see a carbon with a pair of electrons, and you're saying that being connected to a chlorine, with chlorine being an electronegative atom, that it could take those electrons? Meaning we would be generating what structure?
The thing you called it earlier.
The thing I called earlier. A
Carbene.
carbene. What happens?
That goes over there. This goes, trying to be distracted.
Oh, that's interesting looking thing.
That's a doozy.
Little party hat. Do we have chiral atoms in here? Yes, we do have the one that started wedge, so nothing happened there, so don't change it. But where the chemistry occurred on the alkene, we do have chiral atoms, which means I do need to be concerned about those being wedged and that being dashed, or the other way around. Could I say plus an enantiomer? No, because that one never changed. So I can't say plus an enantiomer, it would be a diastereomer. And you can't just say plus diastereomer. You would officially have to draw the structure out. Yeah. There's too many diastereomers to connect. Yeah. Okay. So since we worked through 3, do 4. I'll give you 2 minutes. Okay. If you want to be like, well, we didn't talk about that. Da 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 da. Okay. We'll pick up with 4-membered rings. Okay. What you should do is review the reagents. Look at what those things are. Start to process and think about the patterns within them. That's the goal.